Okay, so everybody hear me well? Would you say yes? Okay, thank you. And welcome back to the course on logic. And what we're gonna do today is we finish off our discussion on first basics of first order logic, and then we will move on to the normal form in first order logic. I mean, some of the normal forms we're going to talk about, you may be familiar with it, such as pre-next form, but scollemization may be something that you haven't heard about it before, unless you study the logic for yourself before. Okay, so where we are. And last time, we talk about, we start to discuss about the first order logic. So this is record. And we said, unlike propositional logic, in first order logic, there are two actors. Two kinds of actors. The one kind of actors are objects, and the other kinds of actors are properties. And then objects are like numbers, and then vertices in a graph, and so on. So these are something concrete that, usually expressed as nouns in English. Properties are really some facts or some claims about objects. So it's all prime, there are infinitely many prime numbers. So that's one properties. And another property is, in particular, maybe, so let's say, KAIST campus is big. This is another property. KAIST campus is an object, and then this property talk about, the properties of this, some fact about or some claims about an object. The reason I talk about, this distinction is because the syntax and semantics of first order logic has essentially two parts. One part is concerned with objects. The other part is concerned with properties. So last time we covered about syntax, and then a little bit of the semantics of first order logic. And for the syntax, we said the syntax is parameterized by so-called signature. And then so it's a bit like first order logic is a very generic programming language, which essentially have two types. One type is a type for object. The other type is type for properties. And usually in first order logic, objects are called terms. Properties are called, the syntactic things for properties are called formulas. So it's like a programming language which have two types, one for objects, one for terms, the other for formulas. And then signature, but it's a bit strange programming language because it's very highly extensible or highly parameterized. So signature is the one that parameterizes this particular programming language studied by in first order logic. And then once signature is given, it decides so-called terms, and also it decides so-called formulas. And then terms are the syntactic entities which can denote objects. Formulas are syntactic entities that can denote properties. Okay? And we said the signature consists of constant symbols, and then function symbols, and then predicate symbols. And all these things together, so they determine what kind of terms we can write in first order logic, also what kind of formulas we can write in first order logic. Constant symbols are like, for number case, it's just a constant objects that we can talk about. So like number 0, 1, 2. Function symbols are operators that we can use to build more sophisticated objects. Like for in the case of first order logic for natural numbers, number theory, we have a plus operation and multiplication operation and so on. For predicate symbols, it's a very basic things that we can use to talk about properties on objects, which are like equality and less than. So this is something that we can use to state some very basic facts. And from this very basic fact, we can construct something more complicated using quantifiers and logical connectives in first order logic. And then we said, just like we have these, there are three things in the syntax. We have three things in the semantic side. For the semantic side, we have something called structure that essentially provide the interpretation of signature. Okay, so structure, you can view it as a meaning of signature, and structure consists of okay. Let's just start with the structure. And we have a structure. Once we have a structure A, so signature is often written as sigma, and that structure induces semantics or interpretation of terms. So if term is T, we now will have interpretations. So this notation means now structure induce how we should map this syntactic entity T into the semantic entity. Okay, which give a meaning. It determines a meaning, mathematical meaning of syntactic entity T. And then also, if we have a formula F, so we now have a so-called satisfaction relation that decides the meaning of this syntactic entity called the formula. Okay, so just like syntax have these three layers, signature, terms, and formulas, we have in the semantic side, we have a structure which provide a meaning for signatures, and then also interpretation of terms, which we're going to talk about soon, also interpretation of formulas. And then last time we talked about structure, and structure consists of 4 parts, actually 5 parts. The first part is called Underline Universe. So this is some specific set which contains all the objects that can be denoted by terms in a first order logic. Okay? So in the number theory, we can typical for the signature of the number theory, for the typical this is underlying universe is a set of natural numbers. And then we also have now we have an interpretation of all the components of the signature. So we have an interpretation for every constant C in the signature. We have its interpretations, which is an element in the underlying universe A. So for instance, so 0 is 0, 1, and 2. These are the symbols. These are the like characters in a programming language. And then structure map that character into mathematical entities called numbers. Okay, so interpretation of this is the character 0 or string 0 is going to be natural number 0. Okay, so it's a natural number. And this is 0. I think the best way to look at it is it's just a string. Okay, it's an ASCII code, string of size 1, whose ASCII code is 0. Okay, so it's a very syntactic, and then what's mapped is a semantic entity that lives in natural numbers. And then the structure specify underlying universe, and then it also provide a meaning for all those constant symbols, and also it provides meaning for all those function symbols like plus and multiplications. So plus now it's meaning. So I think it's written as like this. So its meaning under structure A is going to be functions, mathematical functions defined on this underlying universe. So it's going to be a map from that take two arguments in our underlying universe and return something. So typical common interpretations, it's going to take two numbers n and m and return addition. But it can be something very weird. So it doesn't have to be correspond to plus. It can be something very weird. So another possible options. So this is option 1. But among many other possible options, another option 2 is that if you just take n and m, it may just return n. That's also another legitimate interpretation, although it's very non-standard. I mean, another legitimate part of a structure. Okay. So, and then we also have to provide the meaning for the predicate symbols like equality and less than. So typically less than of A, that's going to be a binary predicate on a binary relation on underlying universe. So it's gonna relate two numbers, n and m, if n is smaller than m. Okay, so this is intended meaning, but if you, so this is a typical option 1. But we can take many different options. This second option is, so this is meaning, I'm gonna say it's exactly the, I mean, anything is related by this guy. So n and m can be anything, any natural numbers. Okay, so that is a very non-standard notion of less than equal. Actually, I think maybe I won't write this bar because it makes things very confusing. Wait. Okay. So this is very unusual meaning of the less than, but this is also another possible option. Okay. So these are the 4 components of structure, but 5th component is, which is very unusual in this lecture. But I think as I said before, my colleagues kind of chose it because it simplifies many notations. So the last component, the 5th component of the structure is going to be a mapping from all the variable to element in the underlying universe. So you will have some mapping, which I think he just write it as A. It's a mapping that maps all the variables to underlying universe of A. So it's one of the components of the, and he writes this mapping as if a variable x and A, that's going to be an element in A. Okay, so the structure consists of these 5 parts: underlying universe, underlying universe, and then the interpretation of constant symbols, interpretation of function symbols, and then interpretation of relational, the predicate symbols. Finally, interpretation of all the variables. And then, as I said, the last part is something a little bit unusual. Typically, when so I'm gonna soon talk about how once we are given a structure, we can now start to talk about, so we can start to talk about semantics of terms induced from the signature sigma. Also, we can talk about semantics of formulas. And then while we are doing this semantics of terms and formula, everything in the structure will be fixed except the last part. Okay, so this last part will keep changing. So sometimes people call the first 4 components as a structure, and the last component is sometimes called environment. But this is the convention that we're gonna take in this lecture. Okay, so this is a reminder of what we did before. So as I said, this is the definition of structure with underlying universe, semantics of constant, semantics of function symbol, and semantics of predicates, and semantics of all the variables. And one important bit is the underlying universe has to be non-empty, And this is some convention we take, which will simplify many of the development. Okay, so maybe something more kind of, I think maybe you already got the idea. So now we're gonna use this structure to provide the semantics of terms and the semantics of the formula. Yeah, the semantics of the terms is typically written as this notation, A of T. So term, it is written as like this. Semantics of formula is written as this notation. I mean, this in Korean, ya sign. And I mean, this is something very common. Whenever you see a sign, so the sign of, right. So if you see sign like this often talk about some fact on proof system. So if you see F and G, it means we can derive G from F using rules in a proof system, but this ya sign, it talk about semantics. So it means according to the semantics, F implies G. So if you have a very strong proof system, these two guys are typically the same, but they are not always the same. For instance, I mean, we are not going to talk about this, but later, if you become interested in Gödel's incompleteness theorem, the Gödel's incompleteness theorem really say for first order logic, for arithmetic, whatever you do, design a proof system. So that will determine what we mean by this. I mean, these notations, the provability. So when F can imply G according to the proof system. Then there also you can easily define the notion of truth. And then the Gödel's incompleteness theorem say whatever you do on the top, you can't really make the top guy and the bottom guy the same. Okay, so that's the Gödel's incompleteness theorem. And anyhow, so the point the reason I bring this up is because I mean this sign is more or almost always gonna be about semantics in logic. And then both definitions will be done. I mean, we talk a little bit about so-called structural induction, which is essentially doing induction on the subcomponent. Like if we have a term, we do the induction on the subterms. If we have a formula, we do the induction on subformula. These are the strategies we're going to adopt to define the semantics in both cases. Okay, so let's see the semantics of terms. Semantics of term is, in both cases, pretty straightforward. Okay, semantics of term. So we are what's given. I mean, if you are not familiar with this type of semantics, just identify what's given and what we have to do. What's given is that we are given structure. Okay, and what we have to do is we have to define a. So this is given. So what we have to do is to define the meaning of all the terms A of T for all terms T. Then what are the general strategies? General strategies, if term is something that's already covered by structure, you just use it, okay? So otherwise, you just define inductively. So that's the general structure, I mean, general form of this, I mean, what general strategy that we can follow. And that strategy leads to this interpretation of terms. Here I call it value of the terms. And then the value of the term will always, for every term T in a first order logic, this value or interpretation of this term is gonna be some elements in the underlying universe in the structure. So this is underlying universe in the structure. And then definition is done inductively. And so so it's done like this. If we have a constant, our structure already tells us what the meaning of a constant should be, what the meaning of constant should be. So we just follow what structure say. So it says the value or interpretation of the constant is exactly the meaning of given to the constant according to the structure. For the variable, we do the same. Our structure, the fifth component, the last component of the structure was the semantics of the assignment, then the semantics of variables. So we just use follow what our structure say and said the meaning of variable x is going to be something determined by which our structure say. So it's x sub a is the meaning given to the variable x by the structure. So this is just follow what the structure A say. Okay, so nothing unusual. But the last bit, we have to do a little bit of work. That's because now we have a term f, and then with the t1 up to tk, and t1 up to tk may be something which is not directly covered by the structure. Then what should we do? We do the induction. Okay, we want to give a meaning to this term which apply function f to term t1 up to tk. Our structure tells us how should we interpret this term, this function application, this function symbol f. So this is coming from our structure. But t1 up to tk may be not a constant, nor it may be neither constant nor variable. So then, that structure doesn't tell us what should we do directly. In that case, we make a recursive call and said we inductively or recursively interpret the argument by using this interpretation. So we give a inductively interpret t1 up to tk, and then look at the meaning of the function symbol in the structure, and then we apply them to these terms. So this is something that if I say, if I give you a structure and then ask you to come up with a sensible but reasonable interpretations of a term t, which is compatible with the structure, and this is what you're going to come up with. So it's something very natural. Okay. And then so this is the interpretation of a term. The interpretation of formula is also, in a sense, straightforward. Now we have this is semantics or interpretation of a formula is given by this satisfaction relation, which sometimes people read it as A satisfies F or A models F, and it's defined inductively. But this inductive definition is exactly what you expect. Base case, which is either true, false, or we have a predicate symbol P applied to term T1 up to TK. In that case, we either use what our structures say, or we just take some basic definition. Okay, so if we have our formula is just predicate P applied to term T1 up to TK. This means T1 up to TK are related by predicate P. And to interpret this, we look at the meaning of predicate symbol P in our structure. So this is coming from structure A. And then we make a recursive call inductive call to get a meaning for term T1 up to Tk. That's already done in the previous slide. So we look at their meanings and see that whether these tuples that we obtain by applying the meaning of the semantics of the term to T1 up to Tk, whether these guys are related by the meaning of the predicate P in our structure. Okay, so P is less than if we have a term T1 and T2. Then what this definition says, we look at the meaning of T1, meaning of T2, and then see whether these two meanings are related by the meaning of less than according to in our structure. And then so that's something that will pop up to you when you want to do something like this. For true and false, conjunction and disjunction and negation, this is very much like the interpretations or semantics that we look for first of all, the propositional logic. Propositional logic. And this is not surprising. That's because propositional logic is really about study on the connectives. And so what we're going to do for true, false, conjunction, disjunction, negation, we just follow what we have done in the propositional logic. True, always the case. False, nothing satisfies false. Conjunction is true if and only if our structure satisfies F. and structure satisfies G, or structure satisfies F, or structure satisfies G. Negation when exactly what you expect. Okay. So we just give you some side remark. There are, as I said, in logic, there are big part of the logic is called proof theory. Another big branch, sub-branch of logic is called model theory. And the godfather of model theory is Tarski. And a very famous proof theorist is called Girard. And what I heard is that Girard make fun of model theory, and he said, he looked at this interpretation by Tarski and see this is too obvious. Some of you might feel exactly the same. He said, oh, this means this is a broccoli is broccoli. So Girard make fun of about Tarski. But anyhow, the point I'm making is that this is obvious and looks very straightforward. And that's because it should be straightforward. This is the semantics that we expect something correspond to our intuitions, then things are done well. If this doesn't go according to our intuition, this means something strange is happening. And then the last case is for existential and universal quantification. We interpret it as essentially existential and universal quantification. We say this for all A satisfy that the structure A satisfy exists X F. This is a syntactic entity, which in some sense doesn't mean anything. But this interpretation say actually this symbol really means existential quantification by saying this is true if and only if there exists some element in our underlying universe such that if we extend or update A by replacing the semantics of variable X by A, small a, then the formula F is going to be true in this updated structure. Okay. And the universal quantification say something very similar, but for universal quantifiers. So it said this structure A satisfies for XF if for every A in the underlying universe of the structure, if we change structure by mapping variable X to small a, then this formula is going to be true there. So let's just really see what's really happening here. Let's think of one case which we assume never happens, but let's think about that things, which is suppose that underlying universe of A is an empty set. This not allowed in our formalism or in our formulation so far. But let's think about this just to see some subtleties of this definition. Okay. Suppose this underlying universe is an empty set. If that is an empty set, our structure will never satisfy exist X dot F for all formula F. Okay, so for every formula, this A is not going to satisfy F. That's because we will never be able to find some element in the underlying universe. Also, another consequence there is for our A, this particular structure is going to satisfy any universally quantified formula. That's because there is nothing in our set. So so this quantification for all A in the U of A, this requirement for every element in A is going to be true vacuously because our underlying universe doesn't contain anything. So the point I'm making is that this definition looks very obvious and looks like no subtleties are going on here, but actually that's not the case. It really depending on what kind of objects. So the syntactic that this exists X dot, this exists X, F, universal X, F, they are just syntactic formulas, but what kind of objects are available in our underlying universe make a huge difference in interpretation of existential and universal quantification. Okay, so Right. So here are a few exercises I want you to do. So based on the interpretation, try to see, I mean, in a sense, try to understand what this formula means in the the sigma structure of the number theory, and check whether you think this formula is true or false. Okay. So let me show you the interpretation here. Okay, so there's a semantics, and then the natural sigma structure. This means underlying universe, the set of natural numbers. And then this interpretation of constant is equal to 0. And one is equal to 1. Plus means really mathematical operation. Plus, yeah. So I think this should be an equality. Really means equality in math. Okay, so if you're using this information to check whether this is true. So I will give you maybe 1 minute to think about this. So I want you to be able to do two things. One is looking at this formula, it becomes like a native speaker of first order language. So you just look at this formula and immediately see what the formula is saying. At the same time, if necessary, I want you to be able to provide the meaning of this, formal meaning of this, by using the definition that we talked about in the previous slide. It's okay. So I'll give you the answer. I mean, the answer is yes. And that's because, I mean, this one says for every natural number, there always exists some natural number y, such that x is either 2 times of y or x is 2 times of y plus 1, which means this means x is even, essentially. And existential quantification and x means this is x is even and this is x is odd. So we know that every natural number is either even or odd. So this statement is true. Okay? And you can, so this is more like, I mean, just the intuitive way of seeing why this satisfaction relation should be true. But you should also, as I said, be able to expand this meaning according to the formal definition. And actually, this using the formal definition is going to be needed when we try to prove relevance lemma that we're going to talk about soon. Okay. So here's another exercise I want you to do. So in this exercise, we are using different signature and structure. So here, the signature we have is, we only have our signature sigma. We only have a binary relation E. Okay. So this is the predicate symbol. and of error T2. And that's it. I mean, there we don't have anything else. And then we have a structure, A. And our structure is this graph. So it's underlying universe. So it's a U of, it has a U of A, and then interpretation of the meaning of this symbol E. Under this, our underlying universe has a 4 element 1, 2, 3, 4. They correspond to the vertices or nodes of this graph. And then E of A is given here. Okay, actually I wrote both of them. So it defines the binary, irreflexive symmetric binary relation defined by this graph. So it's really the representation of the graph as a structure. So now here are two exercises I want you to think about. Think about the both exercises ask you to check whether this particular structure A satisfies the two formulas. The first formula is given like this. Second formula is given like this. So note that in this lecture, the universal quantification has a very high precedence. So really, we are talking about this. And then the second case is not. So universal quantifier binds very tightly. Okay. So I will give you another 1 minute to think about whether the answer for 1 and 2. So okay, so let me give you the answer here. For the first question, the answer is yes. For the second question, the answer is no. The first question said, it's a conjunction of these two formulas. The first part of the first conjunct say for every x, x is not related to itself by the relation E. Okay, and what does that mean? That means this relation is not reflexive, and that is really the case. We don't have if our graph has a cycle like self loop like this, then the first conjunct would have been false, but that's not the case. In our graph, there are no self loop, so this first conjunct is always going to be true. And then the second conjunct in this part say that for every x and y, if x, y are related by E, then yx should be related by E. This means our relation E is symmetric. And that is the case. This E of A is really encoding the symmetric relation expressed by this undirected graph. So this property, the satisfaction relation is going to be true in the first case, but the satisfaction relation in the second case is not going to be true, because what it says for every vertex x and y, we can always find z1 and z2 so that x is related to z1, z1 is related to z2, z2 is related to y. What does that mean? That in terms of a graph, it means that for every vertex x and y, we can find a path from x to y, which is of length 3. So we have a path of length 3. So there are two intermediate vertices. And the first intermediate vertex is called z1. Second is called z2. And then this is not true because if I pick 1 and 3, then we can't really find a path of length 3. If we go path like this, the path is length 2, another path is length 2, and so on. So we can't really come up with a path of length 3. So this 1 and 3 is a counterexample of the claim at the bottom. So this statement is going to be false. Okay. See the next theorem. So here's some final part of this set of this lecture, and this final part is called Relevance Lemma. So we're gonna look at Relevance Lemma and then Substitution Lemma next. What both of them allows us to do is to avoid case analysis or some structural inductions that we typically have to do when you do any kind of reasoning for formulas in first-order logic. Okay, but if we use this relevance lemma, that we can avoid. We can simply we don't have to do any of the. Often we don't have. We can avoid the induction and still prove some interesting properties about the formula. And what this lemma say is something very obvious. So we have a two structure, A and A prime. They are structures over the same signature. Okay, and actually the more generalized version, they don't have to be the same signature, but we have a structure of the same signature sigma. And then we have a formula over the sigma. Okay, and then this A and A prime, if they are the same, then our claim at the end is going to be true, obviously. Our claim we want to make is if A satisfies F precisely when A prime satisfies F. So as far as satisfaction of F is concerned, A and A prime behave exactly the same way. So that's what the conclusion is saying. Okay, so then this is not always the case. So under some condition, only under some condition, this is true. And this relevance lemma talk about that condition. The conditions say the following. It says that A and A prime, they have used the same universe, and then they provide identical interpretations of the predicate symbols and function symbols and constant symbols in the signature. But they may provide a different interpretation for variables, except the ones appearing in F. Okay, so this 1, 2, 3 together say A and A prime are the same, except for the interpretation of variables not appearing free in F. So in A and A prime are the same, essentially almost everything except for the interpretation of variables, which in a sense have nothing to do with F, which doesn't really appear free in the formula F. If that's the case, then the satisfaction of A satisfies F if and only if A prime satisfies F. This is something that you are expecting, but it's going to be very useful lemma that we will use over and over again when we kind of discuss about, say, scolemization and so on. Okay, so what I want you to do now is to prove this lemma. And to prove this lemma, you have to use induction on terms and formulas. So try to prove this lemma. And now to show this lemma, you have to use a structural induction. Let me erase this. But you can prove this lemma in 2 steps. The first step is prove something similar. terms T. So instead of formula for every term T, try to prove something similar using structural induction. And then once you are done, then you can use what you proved in number 1 and prove the lemma using structural induction. So, okay, so I will give you 5 minutes to do this exercise. Okay, maybe it's not quite 5 minutes, but let me just show you the answer here. Okay, so just make it smaller. Okay. Right, so how to prove this? So then I said we're gonna first prove something like this for the terms. So to prove it for a term, so we're gonna think about a version of a lemma where instead of a f, we have a term t. T is a term over sigma. And then we say variable, each variable occurring free in T. And then the final, this is statement, conclusion of the lemma is going to be A of T will be same as A prime of T. So this is the version that we want to prove first. So it's a version of this relevance lemma for terms. And we're gonna use what we proved there to show the relevance lemma for the formulas. And proof for the relevance lemma for the term is quite easy. So relevance lemma for terms. So this proof is by induction. So it's by induction. So then we have to consider the base case. The base cases are T is equal to constant C or T is equal to variable X. But in the constant C, we have A of C, the same as C of its interpretation of the constant in A. But we said A and A prime give the same interpretation for all the constant symbols. So this will be the same. For variables, we said it's going to be interpretation of that variable in A, but X is a free variable appearing in term T. So A and A prime should give exactly the same value. So this is also the case. And then the last case is T is a function application. So then now here, this is inductive case. For the inductive case. Okay. And by induction hypothesis, so we know that A of T1 is equal to, here's an A prime of T1, and so on up to A of Tn, A prime Tn. Why is that? That's because all the free variables appearing in T1, they're gonna be free variable in T. Okay, so every free variable appearing T1 is going to be a free variable in T because T is larger than T1. So if A and A prime give the same value to free variable in T, it should give the same value to all the free variables in T1. Okay, so these conditions on this lemma can continue to hold for all the subterms T1 up to Tn. So that's why we can apply induction hypothesis and we can obtain this conclusion. And then one thing that we know is A and A prime, they assign the same meaning to the function symbol. So thus the semantics of this term T1 to Tn, that is same as f of A applied A of T1 to A of Tn. And this is going to be same as A of f of A prime of T1, A prime Tn. And that coincide with the semantics of these terms according to A prime. Okay, so this concludes the proof of this lemma for the terms. So then we're gonna use okay. So we're proof of the original lemma. So now we go to the proof of original relevance lemma. And then proof is, again, by structural induction. So I'm not going to go through all the cases, but I will cover maybe one or two. So the most important one. So first, think about the base case. There are multiple base cases, true, false, and so on. But one of the base cases, so we have a formula F. The case is formula F is predicate symbol P applied to T1 up to Tn. So the formulas say T1 up to Tn are related by predicate P. And now we said A satisfies this formula F. This is defined by, look at the meaning of T1 up to Tn under A and see whether tuple constructed by these meanings is gonna be related by this relation under A. So that's what this is coming from definition. And then one thing we can do here is that now we know that for every free variable in F, A and A prime say the same thing. And that means for every free variable in T1, A and A prime will say the same thing, and so on. So this tuple will be say exactly the same thing, be the exactly same thing as what I'm gonna write here, because of the reason that I just told you, and then the property that we proved. So this is by lemma for terms. Okay. And then one other thing we know is that we know that by the assumptions of the original relevance lemma, P sub A and P sub A prime are the same. So we can write things like this. So if I just use the definition, this say the same thing as A prime modulus F. So they are the same thing. Okay. So this is a base case. And then inductive case is very easy. I mean, if you just apply the inductions, then you can pretty much cover conjunction case, disjunction case, negation case, and so on. None of them will cause any problem. The only tricky part is dealing with the quantification. So I'm gonna cover one of the inductive case, which about quantification. So suppose if it's universally quantified formula X, I mean for universal quantification X in G. So then we say A models for XG, if and only if. Yeah, I mean, my habit is I used to put dot right after universal or existential quantification. And my colleague, my friend, didn't really use this dot when he prepared the slide. So there may be some mismatch. Sometimes I put dots after the universal quantification, and sometimes I don't. And just I hope that doesn't confuse you. Okay, so this is the definition. And that according to the definition of the semantics of universal quantification, this means A, where X is replaced by this satisfies G for all A in the underlying universe of A. But by the assumption, this U sub A is the same as U sub A prime. Okay, so we can write it like this: satisfies G for all A in U sub A prime. Now, let's think about A. I mean, for specific, this is small a and the structure capital A. Let's think about structure A prime, where small a is still used to update A prime. Okay, so if you compare these two, they again satisfy all the conditions that's mentioned here. A and A prime that will assign the same meaning, use the same underlying universe. They're assigned the same meaning to predicate function and constant symbols in the signature. And for variables appearing, so now for every variable appearing in the original formula, all the free variable appearing in the original formula, they will assign the same value. Furthermore, for variable x, they will assign the same value because that's what we just did here, okay? And now for the formula G, free variables in G are free variables in F or this variable specific quantified variable X. So there are two cases, already free in F or this quantified variable X. For both kinds of free variables, they mean this guy, or something obtained from structure A, the guy below, something obtained from structure A prime, they say exactly the same thing. In other words, the assumptions of the lemma is going to be true for A with this updated A prime, and then formula G. So by this, we know that we can write it like this for all A in use A prime. So then at this point, if you just be packaging it using the definition of satisfaction relation, we get A prime satisfies for X G. Okay. So so here we use so here we use the induction hypothesis. So G is a smaller formula than the one that we started with. So we use the induction hypothesis to replace this part into this part. Okay. So that's the proof. And then the other part of the proof is also quite simple. Okay. So I encourage you to complete the proof because this can be some exercise about the formal, how to do something with the formal semantics. Okay, so that's it for this first order logic part. So in the remaining 10 minutes, I'm gonna give you some overview on the next topic that we're gonna talk about. So if you have do you have any questions, then you can ask me now. Or maybe you can ask me, after 10 minutes. I will stay here for about 5 more minutes. Okay, so the next topic that we're gonna cover is a normal form for first order logic. Okay. So this normal form will play, so some of the normal form that we're gonna talk about, especially pre-next form, it's something that, as I said, you maybe already know in some sense. But score-length form is something perhaps a bit unusual. And score-length form will play a very important role. The first step of automatic theorem prover for first-order logic is to do score-lemmaization. It takes a formula, it converts that formula into a score-length form conceptually, and then after the conceptually, well, really, I forgot, but it does score-lemmaization. That's the first step of the first-order logic theorem prover, and then it checks the property about score-lemmaized formula. Okay, so score-lemmaization is something conceptually not very hard, but it's something that's quite unusual. Which you might haven't heard about it before. So it's a quick recap, but we don't have to talk about this. So let me show you some, give us some, what I mean by the normal form. So the first, to study or design any algorithm for first-order logic is not very easy for many, many reasons. But one of the reasons is that the object, the things that we have to, this algorithm or theoretical analysis have to deal with is quite complex. And it's like formulas in first-order logic can be quite complex. They can have a negation outside, and then existential and universal quantification and so on in the nested manner. And it turns out if I want to do something about some theoretical analysis or designing an algorithm for first-order logic, dealing with formulas like the one that you see on the top line, make things quite complicated. So this it makes our life very, very difficult. On the other hand, if we only focus on specific kind of a formula, especially all the quantifiers are taken outside, that substantially simplify theoretical analysis and practical algorithm design both. Okay, so that's so typical normal form that we're gonna study are all about some specific way of putting this. Yeah, so the converting is about formulas which are of this form, the second kind of form. And then that will allow us to make very simple theoretical analysis and then also the good algorithm design. And right, so and then I think they even have some name for this. So especially, we are not going to look at this, but once you convert the formula into this form where all the quantifiers are taken out, so we have a quantifiers taken out, and then the rest of the formula is the quantifier-free formula is given on the other side, then we can start to talk about complexity of the formula by looking at the alternation of universal and existential quantifier. So if it's everything is universal, it's in some sense not very hard. If everything's universal followed by existential, it's a little bit more difficult. Universal, existential followed by another universal, things get a bit more difficult and so on. So there are some names like sigma and pi and so on in proof theory. But the point I'm making is that if we are somehow managed to focus on, we are allowed to focus on the formulas of the second kind, things become substantially easier. So we're gonna cover in this lecture, in this lecture, is going to be, we will consider the two types of normal form. The one is called Prenex form. What they say is it is a form for the formula where all the quantifiers comes first, like the one in the second example that's shown in the slide. And then we also talk about so-called Scholen form, which is a Prenex form. It's a special kind of Prenex form, which doesn't use any existential quantification. Okay, so this is a Prenex form, but it's not Scholen form. Okay, and then what we will do is that we will look at a few. I will give you I will remind you of some of the equivalences between the first order logic formula that will allow us to convert any formula into Prenex form without changing anything. Okay, by which I mean we will come up with an think about an algorithm that take first order logic formula F. This is the input first order logic formula. And then our algorithm will translate F to some formula G. This is again first order logic formula, but it will be in Prenex form. And I said it doesn't change anything, by which I mean that they too have exactly the same meaning. So which means that we're gonna write this equivalence like this. This means for every structure A, if it satisfies F, if and only if the structure satisfies G. So semantically, they say exactly the same thing. So this is the first step of the normalization process we're going to talk about. But more interesting bit is the second normalization process that take this G and return some G prime. So this is G prime is going to be first order formula in Scholen form. So because it's a Prenex form, it has a quantifier in which potentially alternating universal and existential quantifier. G prime is a Scholen form, so it's not going to have an alternating universal and existential quantifier. Okay, so we will also think about some algorithm to do this. But this algorithm has a very kind of unusual property. So we no longer have G, this is unlikely to be true. I mean, usually this fails. So G and G prime means something different. But this algorithm preserves satisfiability. So if G is satisfiable, if and only if G prime is satisfiable. So this second algorithm is going to be satisfiability preserving transformation. Okay, so we'll look at the first and the second. Right. And maybe in the remaining 4 minutes, so here's something that I want to talk about a little bit and then finish. So just like I said in the previous slide, some key important concept we're gonna use, or some tools we're gonna use, is logical equivalence, which say that if I have two first order logic formula f and g, so if I have two first order logic formula f and g over the same signature, we say they are logically equivalent if no structure A can distinguish between f and g. A satisfies f if and only if A satisfies g. I mean, this is what you expect about the definition of logical equivalence, okay? So it's just, or you can think of this as a semantic equivalence. So that's what this equivalence is telling us. And then the proposition says there are a bunch of equivalences that we can use. And then, so we will actually use when you design a normalization algorithm. The first kind of equivalence is essentially generalization of De Morgan's law, which you, I think, already knows. For all n exist. So it's if you have a negation outside and a universal quantification, I can push negation inside the universal quantification, but universal quantification becomes existential quantification. Situation is exactly symmetric if you have a start with the existential quantification. So that's what the first type of, the equivalence is telling us. Second type of equivalence is say, if I have a universal quantification, so here parenthesis goes like this. And we have something outside, some formula outside that's either combined with conjunction or combined with disjunction. If the formula outside doesn't refer to the quantified variable x at all, then we can move that formula into quantification or outside of quantification. That's equally okay for universal, existential, conjunction, and disjunction. Okay. So if you have a universal quantification like this end can go inside, disjunction also can go inside, as long as G doesn't say anything about X. The same thing for the existential quantification. The third rule say, if you have two universally quantified formula over the same variable, then you can group them together. Same thing for the and then when they combine by conjunctions. The second, same thing applies for existential quantification and disjunction. Roughly speaking, what this rule says is that universal quantification is a generalization of conjunctions. Existential quantification is generalization of disjunction. So that's why they're compatible with each other. The fourth, talk about we can change the order of universal and existential quantification without changing the meaning at all. Okay. De Morgan's law, moving something inside, outside the quantifications, grouping quantifications, and then changing the order. These are the four type of rules. And I think that's the end of today's lecture. Then before finishing, let me mention two things. First, I want to encourage you to do proof this semantic equivalence for this highlighted one. This three red semantic equivalence in your home as an exercise. And second, on Wednesday, we are not going to have any lecture at all. Our lecture will be canceled. On Wednesday is canceled because of graduate admission. I already announced it in the KLMS, but I'm saying it just to make sure you don't miss anything. Okay, so that's it for today, and I will see you on next Monday. So I will stay here 5 more minutes. So, and if you have any questions, feel free to ask me.